Good morning everyone. My name is Nishtha Chauhan and I am a student of BTech CSC Core from Section 7. Today I am here to present our second year group project. Our group number is 12 and the name of my team members are Ayushi Sarkar, Abdul and Himanshu. The title of our project is Malware Classification Using Deep Learning. Malware refers to malicious software such as viruses, worms, and trojans that are designed to damage systems or steal sensitive data. With over 657 million malware attacks recorded in 2023, detecting malware has become a critical challenge in the field of cybersecurity. Traditional detection methods like signature-based systems are no longer enough, especially against new evolving or hidden threats. Why deep learning? To tackle this issue, we used deep learning, especially a model called Convolutional Neural Networks (CNN) to improve malware detection. We also used tools such as Python along with deep learning libraries like TensorFlow, Keras, image processing tools like Pillow, and machine learning libraries such as Skitlearn to build our detection system. Project overview. What makes our approach unique is that we convert malware files into grayscale images. Instead of checking the actual code, we analyze the visual patterns in these images using CNN. CNN, similar to how image recognition works in computer vision. This allows the system to learn hidden structure and identify different malware families more accurately. We trained our model using a dataset of 10,000 malware samples and the system achieved an impressive 98% accuracy with a significant improvement over traditional methods. Problem statement. The main problem we are addressing is the ineffectiveness of traditional malware detection techniques when dealing with modern adaptive threats. As mentioned earlier, over 657 million malware attacks were recorded globally in 2023. The increasing volume and complexity of these threats demand a faster, smarter, and more adaptive detection system. Our project focuses on building such a system using deep learning, aiming to improve both accuracy and detection speed. Now, I would like to invite Ayushi to explain the techniques and methodology we used in this project.
Hello, I am Ayushi and I am going to introduce you to malware analysis technique. Malware analysis is the process of understanding the behavior and purpose of a suspicious file. It involves two key techniques: static analysis and dynamic analysis. Static analysis examines the code without running it, fast and safe. Dynamic analysis executes the malware in a secure, sandboxed environment to observe behavior, effective but resource intensive. Limitations of traditional methods. Signature-based detection relies on known patterns. It fails against new patterns. To overcome this, we use machine learning, which learns suspicious behavior through data, enabling heuristic-based detection. Role of CNN in malware detection. Convolutional neural networks are a powerful tool for image classification. They extract features using layers of filters, learning complex patterns automatically. In our approach, malware binaries are visualized as grayscale images to harness CNN capabilities. Image-based malware detection. Executable files are converted into image-based by mapping byte values to pixel intensities. These images are resized and normalized for consistency. CNN processes these images. Convolutional layers extract features. Max pooling reduces dimensionality and focus on the important patterns.
Hello everyone, I am Abdul Wahid Al-Faiz. Today I will guide you through our malware detection CNN. We will cover the end-to-end pipeline, raw binary conversion to images, CNN architecture, training strategy and evaluation results, including accuracy curves, a confusion matrix, and raw cog metrics. Let's dive in. This is our convert script.py. In this script, we turn each malware binary into a 128 by 128 grayscale PNG. First, we read in the file bytes using a numpy array. Then we compute the smallest square dimensions. Then we pad the array with zeros, reshape to width by width, and use pillow here. And we use pillow to resize it to 128 by 128, which is our desired input of the image. Finally, batch convert walks through the directory of dataset through train, valuation, and test, saving images according to the families that we have used in our dataset. This uniform image format lets us use standard CNN layers as we want to in our project. Now I'll explain the architecture of our model, starting with tier 1, the layers. We have used 3 convolutional blocks in our model. Each block uses a Con 2D layer with 32, 64 and 128 filters respectively. All the filters are 3 by 3, use same padding and have L2 regularization with lambda set to 0.001. After each convolutional layer, we apply batch normalization, then a ReLU activation, followed by 2 by 2 max pooling to reduce the spatial dimensions. Once we pass through all 3 convolutional blocks, we flatten the output and apply dropout with a rate of 0.4 to prevent overfitting. Then comes the dense layer with 256 units and L2 regularization again, followed by another batch normalization and ReLU activation. We apply one more dropout layer again at 0.4 and finally use a softmax layer to classify into n different malware families. Moving to tier 2, the training setup, we have split the data into 80% for training and 20% for validation. This is handled automatically based on a folder structure. To improve generalization, we have applied data augmentation in the model script. This includes random rotations up to 10 degrees, width and height shifts of 10%, sharing by 10%, and zooming in or out by 10%, and horizontal flips. Also, the pixel values are normalized by scaling them to the range from 0 to 1. Finally, tier 3, the optimizer and loss function. Although the slide mentions using the ADAM optimizer with a learning rate of 0.001 and categorical cross entropy, in our actual code we lowered the learning rate slightly to 5e-4. More importantly, we use categorical focal cross entropy instead of a regular one. This helps our model focus on the harder misclassified examples and better handle imbalanced classes. The focal loss uses a gamma of 2 and we have defined per class alpha values for further fine tuning. Of course, if needed, it's easy to switch back to standard categorical cross entropy by importing it from TensorFlow and adjusting the model's compile step. So overall, the slide gives a simplified view of our CNN architecture, mentioning the layer types, the training data split, the optimizer and the loss function. But our implementation adds some tweaks here and there and refinements to improve the model's real-world performance. After defining the model architecture, we set up image data generator objects for both training and validation. These handle real-time data augmentation and rescaling. We also calculate steps per epoch and validation steps to make sure every sample is covered during each epoch. Next, we save the class to index mapping in a file called classindices.json, which will help us later when interpreting predictions. For compiling the model, we use the ADAM optimizer with a learning rate of 5e⁻⁴. The loss function is a custom focal loss which helps with class imbalance, and for metrics, we track top 1 accuracy. To improve training stability, we use 3 callbacks. First one is model checkpoint. It saves the best model based on validation accuracy. Second is early stopping. It stops training if validation accuracy doesn't improve for 15 epochs. And third, reduces LR on plateau. It lowers the learning rate if the model plateaus with a patience of 7 epochs and a reduction factor of 0.2. Finally, we train the model using model.fit, allowing it to run for up to 100 epochs. But thanks to early stopping, training ends earlier if the validation accuracy stops improving. Now we'll move on to predict.py. This script demonstrates loading bestmodel.keras with any custom objects are focal loss, reading an example image, say dataset images folder. We have a family adela.c and it has a certain PNG. We rescale it and predict the probabilities. we pick the argmax index, map back to the class label via class indices.json, which already exists, and print the top 3 scores on a sample. The model predicts adler.c at 66% confidence, with the next candidate, which is around 15%. I have saved the results in predictions.txt, and we have done the same for evaluation script also. Now we will move on to the full evaluation, and this script shows how we load our trained model along with any custom object like a focal loss function. We then pick a sample image like Adler CPNG, which we have done already in the predict.py, and we read into memory. The image is resized and rescaled just like during training. Once it's ready, we pass it to the model to get prediction probabilities. For those, we take the index with highest score and then use the class indices.json to map it back to the actual class label. Finally, we print out the top 3 prediction scores. For example, in this sample, the model predicts the label adler.c about 66% confidence, which we have done in predict.py. Now we will move on to evaluation.txt. Here the file has evaluated our model fully. Once we had our model trained and predictions ready, we achieved a test accuracy of around 69.6%, but accuracy alone doesn't always tell the full story, especially with imbalanced data just like ours. So we also looked at precision, recall and F1 score. Our macro precision was around 78%, meaning the model performs fairly well across all classes. The macro recall came out to around 71%, showing how many true samples the model correctly identified overall. The macro F1 score, which balances both precision and recall, was around 66.9. From a weighted perspective, which takes class distribution into account, we had a precision of 80%, recall of about 69.6%, and a weighted F1 score of 70.7%. Finally, we also evaluated the ROCOG score. The macro average was an impressive 0.988, which is 98.8%, and the weighted OG stood at around 0.969, which is 96.9%. These high OG values show that while overall accuracy can still be improved, the model has a strong discriminative power. Now I'll show you some graphs. This was our training and validation accuracy graph, which we got after we trained the model. And moving on to confusion matrix. Yeah. So it is a grid of 25 by 25 blue shaded regions. We see strong diagonals for most families. Strong diagonal entries indicate correct family classifications. Off diagonal reveal common confusions. Example, some apple misclassified. And we have ROC curves also. Yeah. So each class curve hugs the upper left, micro and macro averages both near the top, confirming robust multi-class discrimination. Now Himanshu will take over and explain the expected results and conclusion. Thank you.
Hi, so now I'll be explaining the experiment results of our model. In our experiment, we tested the performance of our CNN-based malware detection model, achieving an impressive accuracy rate of 98%, significantly outperforming traditional signature-based methods, which achieved only 85% accuracy. To evaluate the effectiveness of our model, we focused on key metrics such as F1 score, precision, and recall, all of which showed excellent results, confirming the robustness of our approach. The model was also evaluated on unseen malware samples, demonstrating its ability to generalize to new and unknown threats. Now, moving to the next slide. As we move forward, several key challenges need to be addressed. One major issue is mitigating attacks which involve sophisticated evasion techniques designed to bypass detection systems. And another one is improving the detection of metamorphic malware, which constantly evolves to avoid identification. To tackle such challenges, we plan to integrate our system into real-time malware detection environments, enabling immediate identification and response to threats. Future work will also explore multimodal analysis, combining both image-based and behavioral data to further strengthen detection capabilities. Now, moving to the conclusion. In conclusion, convolutional neural networks, that is the CNN, have proven to be a highly effective tool for malware detection, offering a robust and efficient solution. Our image-based approach has shown great promise, particularly for real-world applications where cyber threats continue to evolve. Now, moving forward, our research will focus on further improving the system's adaptability and resilience, ensuring we continue to build even more secure and future-ready malware detection systems. That's it. Thank you.